Welcome to the final lesson in combinatorics. In this lesson I have several exercises based on the principles and theorems that I covered in the earlier lessons in this playlist. Some of the exercises are fairly easy and a few are difficult, but I provide hints in all cases, and I also provide solutions for all the problems. All right, let's look at our first problem. This one's, I think, pretty easy, but let's have a look at it. For a particular car model, one can choose 7 exterior colors, 3 interior treatments, and 5 packages of options. How many possible combinations are there? And I even give a hint here, use the product rule. Okay, so I'll give you the solution on this slide. If you want to try it, pause now. Okay, I'm back. So here's the solution. I kind of gave it away. It's just a matter of using the product rule. So 7 times 3 times 5. You pick one out of the 7, one out of the 3, and one out of the 5. And then it gives you 105 possibilities. Okay, let's proceed to the next one. Find the number of proper divisors of 1,397,550, where proper divisor of a positive integer n is any divisor other than 1 and n itself. So if I give you 7, that's a prime number, so proper divisors would be 0, there aren't any. If I said, let's take 6. So proper divisors of 6 would be 2 and 3, but we would exclude 1 and 6 just by the definition of proper divisor. Okay, so this is a bigger number, and obviously we can't just look at it and get the answers. We need to do some analysis. I'm going to first give you a hint, and that'll kind of give it away, but then after the hint, I'll actually give you the answer. So if you don't want the hint, you may want to pause right here and give it a try. Okay, I'm going to give you the hint now. So here it is. You may have guessed this, that the trick is to factor this. And I've done that for you here. It's 2 times 3 times 5 squared times 7. I could have put 2 to the 1 and 3 to the 1 here actually. Times 11 cubed. And remember to subtract 2 since 1 and n are not proper divisors. I already kind of went through that. All right, so again, if you want to give it a try from this point, pause the video, and I'll come back in a second and give you the answer. Okay, so here's the answer. For each one of these numbers in the factorization, you have multiple choices. Either you can have 2 in the factor or not, so that gives you 2. Same for 3. 3 could appear or not in the factor of this large number. Then for 5, we have 3 choices, right? It could either be 5 to the 0, 5 to the 1, or 5 squared. And then 7 is just 1, either 7 to the 0 or 7 to the first power. And then there's 4 possibilities for the for the 11. And then we need to subtract 2. So we have 2 times 2 times 3 times 2 times 4 minus 2. And that gives us a solution of 94. So this is similar to the previous problem, except it's stated more generally. So we have an integer n whose prime factorization is shown here. So you have p1, p2, pr, the prime factors, and these are the powers at which the prime factors are raised to. And the question is, determine the number of proper divisors. So I'm going to give you the solution right after this. So if you want to give it a try first, hit the pause button. Otherwise, I'll come back in a second. Okay, so here's the trick, and it's basically what we've done in the previous slide, but more generally here. So you just take the powers and you add 1 to each of them, and then you multiply them and subtract 2. And again, the idea is that if you're looking for a factor of this number, you can take each of these powers to any either 0 power up to all the way up to the power that this is raised to, and you have that. That's why you have the +1 there, because you can have it to the 0 power. You basically don't have that in the factorization. Okay, so let's continue. I have quite a few more problems. This one's a bit harder. I'll give you a hint once I read this. So prove that if A is any subset with 8 elements from the set from 0 to 12, then there are 2 elements of A whose sum is 12. Or perhaps I should have said at least 2 elements of A whose sum is 12. Okay, so I want to give you the hint. So if you don't want it, you want to pause right here. Okay, so here's the hint. Use the pigeonhole principle. Now I'll give you the hint in more detail. This kind of almost gives it away. So as I say, use the pigeonhole principle. Then the next trick is to use this as the pigeonholes. H1, using H for hole, is 0, 12. So you notice the sum of these two is 12. The sum of these two is 12, so on. Then H7 is just 6. We run out of pairs because there's 13 numbers in here. So you're picking 8 elements. So what's the worst case to avoid having a sum of 12 here? So the worst you could do is pick 1 from here, 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 1 from here. That's 7. So you could possibly pick 7 numbers and not have any 2 of them add up to 12. But if you pick that 8th number, there's no choice. It has to come from one of these sets here, and then that forces you to have 2 numbers that add up to 12. Now, of course, if you picked this and this and this and this and this and this, and if you picked, say, all these as your 8 selections, then you would have more than 2 elements that add up to 12. So I should have said at least here, but you get the idea. Okay, so this was something I discussed in several lessons back, the pigeonhole principle and various variations of that. Our next problem is rather difficult, at least in my opinion. If 17 points are chosen at random in the interior of an equilateral triangle, each side of which is 4 units long, show that some pair of points are within 1 unit of each other. I'll give you a hint. Use the pigeonhole principle. Okay, so if you want to try it, pause now, otherwise I'm going to come back in a second. All right, so here's the trick. You divide the triangle, the big triangle, into 16 smaller triangles. Each one of these is 1 by 1 by 1, equilateral triangle of side length 1. And then, since there's 16 of these, and you can avoid having 2 points within 1 unit of each other if you just put 1 point in each of these. Okay, so that's improbable, but it's possible. So that would, the question is, well, when are you actually forced to have 2 in the same, within 1 unit of each other? And that's when you hit that 17th point, you're going to have to put it in the same triangle as where one of the other points are. And that's the worst case. Of course, it could happen sooner, but this is the minimum where you're forced to have 2 points within 1 unit of each other. Now, there's a bit of a wrinkle. You may ask, well, what if the point falls on one of these horizontal lines or one of these slanted lines or one of the intersection points? So we have to assign it or agree what triangle the point is in. And there's 2 ways, or at least 2 ways of doing that. So one way is to define ownership. So if you fall on a horizontal line, we'll just define the point to be in the triangle above. If we fall on one of these slanted lines, we'll say that the point is considered to be in the triangle to the left. And if you fall on one of the intersection points, even down here, we'll just say it's to the triangle to the left and up. And that would give us a clear indication of where any of the points fall in terms of which triangle. Another approach is if a point falls on the boundary between any two or more small triangles, we arbitrarily assign it to any one of those triangles. That'll also work. This is kind of more deterministic, and this is not. Okay, so if you figured this out, you're doing well. I didn't. I had to look it up, and I think this is probably the hardest one in the entire list of exercises. So let's continue. We have two problems on this slide. They're kind of similar. How many ways can we arrange the letters shown here? And this is an application of the labeling principle, which I went over in a previous lesson in a lot of detail. So I'll assume you're familiar with that, in which case the answer is pretty automatic. And then the second problem is how many three-letter words can be formed from the letters D, D, G, G, G. I'll give you the solution in a second on this slide. If you want to try it, pause the video now. Okay, so from the labeling principle, we take the total number of letters, 9 factorial. Then we need to divide out the two D's, that's 2 factorial, and the 3 G's, that's 3 factorial. Again, I explained why this works in my previous lesson. I don't want to repeat it here, so I would refer you back to that lesson on the labeling principle. And then we just divide the 2 factorial and the 3 factorial and the 9 factorial. That cancels out the 2 and the 6, and you're left with these numbers. You multiply them and you get 30,240. Then the second one, you just take cases here of how many G's you have. First case is you have 3 G's. There's only one arrangement there. Then you have 2 G's and 1 D. So it could be a D here, a D in the middle, or the D up front. And then you could have 1 G and 2 D's, and then you have a G here, a G in the middle, or a G at the front, and they're the only 7 possibilities. How many 5-letter words can be formed from the letters AA, BBB, DE? So this may not be the hardest problem in the lesson, but it's probably the most tedious. There's a lot of cases and subcases in order to figure this out. So I'll give you a chance to work on this. So you may want to pause here, and then I'll come back and give you the solution. So I'll give you a hint first. To find the number of 5 distinct letter sequences, consider cases based on whether D and or E are included, since each can appear at most once. Okay, so that'll help, I hope, divide things into cases that you can work through. All right, so let's look at the answer. There are 3 main cases here. Neither D nor E, so you just have AA, BBB as your 5 letters, and then you have to figure out the arrangements there. Then you have exactly 1 D or 1 E, so it's symmetric, and we'll compute it for one of the 2 subcases, and then we'll multiply by 2. And then the third case is where you have both a D and an E included in the 5 letters, and then there's several subcases there also. Then we'll add all these cases together and we'll get the answer of 250. But let's look through them. So the first one, well, there's no D or E, so that's a labeling problem where you have AA, BBB, and so you take the number of letters, 5 factorial, and then you divide out the repeated A's and the B's, 2 factorial and 3 factorial. And the 5 factorial is 120. This is 2 times 6 is 12. So you get 10. Okay, then we go to case 2, where exactly a D or an E is included, not both. So you can have 1A, 3 B's, and then a D or an E. So that's 5 again. And then you're using the labeling principle here, 1 factorial, 3 factorial, 1 factorial, and you get 20. And that's whether it's a D or an E that's included, so that you really have to multiply this by 2, which I do at the end here. And then you have the other case where you have 2 A's, 2 B's, and then either a D or an E. And that's 5 factorial divided by 2 factorial, 2 factorial. And you get 120 divided by 4, that's 30. And you add those to get 50. But again, these cases are duplicated whether you have a D or an E, so you have to multiply by 2. So there's 100 possibilities in this case. Then you have the third case where both the D and the E are included in the 5 letters. And then you can have subcases based on the number of A's. So the first case we have 3 B's, a D, and an E. So we get 5 factorial divided by 3 factorial times 1. I didn't bother to put in the 1 factorial and the 1 factorial, but you just get this here. That's 20 if you work through that. Then you have 1A, 2 B's, 1 D, and 1 E. So you have a 2 factorial in the denominator, as well as 1 factorial, 1 factorial, 1 factorial, but that's just 1. You get 60. And then you have 2 A's, 1 B, 1 D, 1 E. And that's 5 factorial divided by 2 factorial, or 60. And you add those and you get 140. And so we have 10, 100, and 140, and we get 250. From the set of integers from 1 to 30 inclusive, how many ways are there to select 3 even numbers and 4 odd numbers? If you want to give it a try, pause now. I'm going to give you a hint first, then I'll give you another chance to pause, and then I'll come back and give you the answer. Okay, so here's the hint. Use the labeling principle to determine the number of ways of separately selecting the even and odd numbers out of 1 to 30, and then use the product rule. Okay, so I'm going to show you the solution now. So the number of ways to select 3 even numbers out of the set from 1 to 30. So there's 15 even numbers. And we want to choose 3 of them, and then the other 12 are not chosen. So we have this formula here. And I just, 12 factorial cancels most of 15 other than 13, 14, and 15. Then you have 3 factorial. And when you divide this out, you get 455. Then similar for the 4 odd, you have 15 odd numbers. You select 4 out of those, and then 11 you do not select. You get this here. You get 1365, and you multiply, and you get 621,075. How many 6-digit numbers have exactly 1, 2, and 1, 7? So if you want to pause and give it a try, do so. Otherwise, I'm going to come back and give you the solution. I'll give you a little bit of a hint. You can break this into 2 parts. First part is just figuring out how many ways you can find the positions for the 2 and the 7. And then computing the number of ways that the other 4 positions can be filled by the numbers other than 2 and 7. Let's look at the answer. So use the labeling principle to determine the number of ways of selecting 1 spot for 2, 1 spot for 7, and 4 spots for the other the numbers other than 2 and 7. So that's this part here. 6 factorial, that's for the 6 digits, and then you one spot for the 2, one spot for the 7, and then 4 spots for the numbers other than 2 and 7. Then next, multiply times the number of ways of putting the other 8 numbers, in other words, not 2 or 7, in the other 4 spots. So that would be, you have a choice from the other any one of the other 8 numbers in those 4 spots. So it's 8 to the 4th power. So you multiply these two together, and you get 122,880. All right, we have one more slide in this lesson, which I'll get to in a second. This is a bit open-ended, and I don't really have an answer for you for the different problems, but I'm kind of giving you some possibilities for more problems to work on. And that's poker probabilities. If you go to the Wikipedia article, poker probability, they have the probabilities for the different hands, but they also have the frequency. So this is what we've been counting. Here's one that's easy to do in your head. The royal flush is 10, Jack, Queen, King, Ace. I know this is a bit small, but if you go to the Wikipedia article, you'll see these a bit bigger. And so you could have this for any of the 4 suits. So there's 4 possibilities there. Then you have a straight flush. So all the cards are of the same suit, and you start from one number, and then you proceed incrementally, 5 up to 5 units above, and that's 36 possibilities. And there's many more. I just showed you the part of what's on this slide here. So you can try that. You can just look at the hand and how it's defined, and then you can work on the solution and check your answer with this frequency. These probabilities are just the total number of poker hands divided into the number you come up with here. So these are quite small, as you would expect, right? There's only 4 ways of getting a royal flush, but there's many, many ways of getting any poker hand, 5 cards. And then what's nice is they also have the formula that they use to do the different computations. They don't explain how they got the formula, but it's certainly a strong clue. So they spell that out here in that one column. And there's quite a few, I don't know, there's over a dozen different hands on that page. So a whole bunch of problems for you to try. And as you can just see, just from these 3, there's different things going on here. Product rule, and then having to subtract some things to do the bookkeeping correctly. And the -4 is because it says excluding the royal flush. That's why they had to subtract the 4 from this here. Then here you have another product rule example. Okay, so that was it. That was the last slide in this lesson, and the last lesson in my playlist on combinatorics. I'm thinking about some other playlists, maybe graph theory, but I haven't decided yet. In any event, if you like this, please give it a thumbs up and stay tuned. I'm sure I'll be having more videos at some point.